Today we're looking at sequences. My understanding is that you have already seen sequences with Mrs. Stevens, so this should also be a review. All we're doing are these two sections. We're doing 9.4 and 9.5 out of Chapter 9, and that is it. And then testing on it next week. The test will have, obviously, Chapter 9 stuff, and then probably a handful of other questions from other tests. Okay? But it should be shorter. All right, so we're looking at sequences. This includes infinite and finite sequences. We're looking at limits of infinite sequences. We'll need that in the next section. Arithmetic and geometric are the two biggest types that we're looking at. And then we'll also look at how do you graph a sequence on your graphing calculator. So a sequence. An infinite sequence is a function whose domain is the set of positive integers 1, 2, 3, 4, 5, blah, 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 going on forever. Basically what that means is that it doesn't mean that the sequence itself is 1, 2, 3, 4, 5. It just means that you have a pattern for the first term, the second term, the third term, the fourth term. That's what that means. And then infinite means that it just keeps on going on that pattern forever and ever. A finite sequence is basically the same exact thing, except for instead of going on and on forever, we have an ending point somewhere down the road. So in other words, you have n terms in your sequence rather than it going on forever. So let's look at the first example. There's two different ways that a sequence can be defined. The first way is explicitly. This is a harder way to come up with if I give you the actual sequence, but it's easier going the other way around. So it's easiest to write the numbers in a sequence if I give you the explicit formula, and I'll tell you why. The other type of formula is going to be a recursive formula. That one is harder to get all of the numbers in the sequence, but vice versa, it's easier to write if you know the sequence and are writing the formula. And you'll see that in a couple of slides. So for the first one, we're asked to find the first through fourth terms and then the 10th and the 15th term. So all you have to do here is notice that this input is just the sub number. So in other words, whatever term you're on in your sequence, that's what you're plugging in, right? So if I'm trying to find a sub 1, then I'm plugging in 3 times 1 plus 2, which is 5, right? For a sub 2, what am I going to plug in? What is it going to look like? What? Come on, guys. What is it going to look like? This is not that hard. Thank you. And that equals 8. A times 3, or a sub 3. Yep, 3 times 3 plus 2, which equals 11. What is a sub 4 going to look like? Okay. Which is 14. So those are the first 4 terms. Okay, then I want you to jump down and find the 10th term. So what do I do for that? Yeah, this I know is sounding very repetitive. It's not too difficult, right? And then we go down a little bit more to a sub 15, and that's going to be 3 times 15 plus 2, which is going to be 47. Very good. Are there any questions on that? Okay. Let's look at the next one. The next one has kind of a nifty little trick to it with that -1 to the n minus 1. Okay, so the first thing we want to recognize is, again, you're taking your sub number and you're plugging it in here, but you're also plugging it in here, right? So you're plugging it in for a power, and then you're plugging it in for a multiplier. So when I plug in a sub 1, I get-- to the 1 minus 1. But what's that's going to be? to the 0, right? Times 3 times 1 minus 5. So the first thing you want to pay attention to is how does this affect your function. All that this is going to do is alternate your terms from positive to negative, or the opposite of what they were originally going to be. When you have an odd power up here, you're going to keep the negative, right? But when you have an even power, what's going to happen? It's going to go away, right? So every other term is going to be multiplied by -1. Okay? Now here, notice that 3 minus 5 is -2, right? So this value happens to be negative, and then since this is to the 0 power, this doesn't change anything for this particular case, so it's -2. So now let's look at a sub 2. That's going to be -1 to the 2 minus 1, which will be 1, times 3 times 2 minus 5. So 3 times 2 minus 5 is 1, but then we're going to make it negative because this time I do get that negative value with an odd power, right? So that's going to change to a -1. Let's take a look at a sub 3. So a sub 3 is going to be -1 to the 3 minus 1, which will be squared, times 3 times 3 minus 5. So this stuff is all 4. Do I make it negative this time? No, because -1 squared loses the negative, right? So this is just 3 minus 5, which is 4. And the fourth term, -1 to the 4 minus 1 will be cubed, and then 3 times 4 minus 5. So that equals 7, and then do I give it a negative? Yes, because -1 cubed does retain the negative, so -7. Jump down just a few terms to a sub 10. That's going to be -1 to the 9th, good, times 3 times 10 minus 5. So that's going to be 25, and then do I give it a negative? Yes, I do, because that is an odd power on the -1. And then jump down just a few more terms to a sub 15. That's -1 to the 14th times 3 times 15 minus 5. So that's 40. And do I give it a negative? Not in this case, right? Because it's to an even power on the -1. All right, are there any questions how to find numbers in a sequence using an explicit formula? No? Okay, so before I move on to the next slide, I just want to point out, this is explicit because all I need to know is which number, like how many terms into the sequence I am, and I can just plug in, like if I want to know what the 10th term is, then I can just plug in 10 somewhere in my formula and get it, right? That's explicit. That means that I can jump to any term in the sequence and find it. But sometimes formulas are defined recursively. In other words, instead of saying, hey, if I want the 10th term, I can just plug in 10, it's defined based on the numbers previous to it. So you'd have to know what like the numbers in the sequence were before it in order to define it. So that looks like this. And again, this is recursive. So this time you will notice that I am not plugging in just n anymore. I am plugging in a sub n, which means I'm plugging in the actual term previous to this one. Notice that this says a sub n plus 1, so that means whatever number I am in the sequence, n was just right before it, right? And so what I would do is take the actual value of that term and plug it in. That means I have to know the value of the previous term. I can't just jump around on this. So like if I wanted to find the 10th term, what do I have to know? I have to know what the 9th term's value was, right? Does everyone see that? Okay, so you'll notice that that also means I have to give you a starting point. So here I'm giving you a sub 1 because I can't just have you find a sub 1 without the term before it, right? So the starting point is that they'll give you a sub 1, and then you use a sub 1 to find a sub 2, right? So if I do this, I am finding a sub 2, which is going to equal 1 plus 3 times a sub the one previous to it. Not just 1, though, the actual value of a sub 1, right? So you're taking and plugging in the value of a sub 1. Okay, so that's going to be 1 plus 3 times 2 equals 7, right? Notice that I didn't plug in 2 here because it was the second term. I plugged in 2 because a sub 1 happened to be 2. So now watch what happens for a sub 3. When I do a sub 3, I'm going to be doing 1 plus 3 times a sub 2. And again, you're taking, so I want a sub 2, but I know that a sub 2 was 7, right? So now I'm not plugging in what number in the sequence, I'm plugging in the number of the sequence before. So 1 times 3, or 1 plus 3 times 7, which is going to be 22. Okay? So then when we jump down to a sub 4, that's 1 plus 3 times a sub 3. And again, I'm plugging this value in from the previous term. So that ends up being 1 plus 3 times 22, which is going to be 67, right? So now you'll notice that I only wanted the first 4 terms. I've done that. Why can't I jump down and just find a sub 10? Because I don't know a sub 9. So that's the fallback of a recursive formula, is that you do have to know the numbers previous to it. You can't just jump all over the place, right? Any questions on difference between explicit and recursive? No? Okay. So the next thing we're going to look at is finding the limit of a sequence. So there are certain sequences that as you go through the numbers in the sequence, the numbers are just going to grow and grow and grow and grow to get bigger and bigger and bigger, and there is no limit to them, right? They just keep on going out to infinity. But there are sequences out there that instead of growing, reduce, but not by subtraction. So for an example, if I kept on taking half of something, so if I started with 4, and I took half of 4, where would I go to? 2. And if I took half of 2? 1. And if I took half of 1? Half. Half of a half? So on and so forth. What number are you going to get closer to but never ever cross? 0. So that would be an example of a sequence that has a limit, that it has this number that it can never actually cross, but that it's getting closer and closer to, right? And so we have special terms for sequences that do these things. If the limit of is a finite number, so if you can actually say the limit of this number is 0, or the limit of this sequence is 2, so you can actually pinpoint where that sequence is going to, then you call it convergent. It converges to that number. If, however, the limit is infinite or does not exist, then you would say that the sequence diverges. Examples of limits that are infinite are, like if I take the number 7 and then add 5 and add 5 and add 5 and the sequence is just to keep on adding 5, is that ever going to stop any place? Or is it just going to go to infinity? It's going to keep on going to infinity. So that is an example of an infinite limit. An example of a limit that wouldn't exist, if you guys can think back to that first example we did with the -1 to a power, right? That sequence was jumping back and forth between positive and negative numbers, wasn't it? So can that really, I mean, in special cases it is possible for that to converge, but if it's jumping back and forth between positive and negative numbers and it's growing out to infinity in both directions, that technically doesn't have a limit because it's not technically going to positive infinity all the time or negative infinity all the time. Does that make sense? So that would be an example of a limit that wouldn't exist. All right. The way that you want to deal with these when you're finding the limit, and I'm just doing really basic ones with you guys, but you're basically finding if there is a horizontal asymptote for the function, for the most basic ones. Now, I'm not going to give you any of the harder ones where you have to do other strategies, but you guys basically are going to know that when you're finding the limit as n approaches infinity, you're actually finding whether or not that thing has a horizontal asymptote, and if so, where. So let's review those rules real quick. First of all, for this very first one, you have to actually write what the sequence is for this one. You might be able to already tell what it converges to, but let's write it out anyway. So if I were to write the limit as n approaches infinity, and I wanted to write this sequence in terms of a pattern, what is the pattern here? One over n squared, right? So for an example, if I'm on my first term, I would plug in 1 and square it, and that would give me 1 over 1. If I plug in the second term, 1 over 2 squared, 1 over 3 squared, right? So that's definitely the pattern that's happening here. Now let's think about when it's in this form, when you have a higher power in the denominator, what did that mean about your horizontal asymptote? What was it? Huh? So you guys have to think back a little ways. Higher power in the denominator means your horizontal asymptote is 0. Very good. So you're going to have to recall those rules. That means that since this has a limit that's a number, you can say that this thing is convergent to 0. For this sequence, we don't have to come up with the pattern. They've already given it to us. So all we have to do is consider what is the limit of this thing. So what do we notice about the power in the top and the bottom? They are, highest powers are the same, right? So what is your asymptote when the highest powers are the same? A over b, so in this case, what? What's your a value on top? Over? But negative, right? So I'll tack that on in front. So that means that this one also has a limit, and this one is also convergent or converges to that value, negative 3/5. And then remember, if you have a power that's higher on top, if the degree is greater in the numerator, then what does it go to? So let me give you an example of something like that. So let's say that I wanted you to do the limit as n approaches infinity of 2x minus 5. So that's not even a fraction, but it does technically have a higher degree in the numerator, right, if that's over 1. So what is that limit? Infinity does not exist, right? And so what would you say about this guy? That it diverges. Very good. Okay, any questions about finding limits of sequences and the convergent divergent stuff? Yes, Lauren?
Do you need to say that it diverges to infinity, or is that just...
No, you just say it diverges and that's it. Okay? So let's kind of do a prequel to what the next couple slides are going to be about. I'm asking you to predict the term or the nth term, the general term or the nth term of each sequence. So if I asked you to find a formula for the next term down the road, how would you do this? So let's first do, this is where recursive is better, right? So if I said I wanted to find a sub n, how could you tell me to use the previous term? So first of all, how would I write the previous term in general? If I'm looking for a sub n, what is the term right before it? A sub n minus 1, right? And what do I want to add to a sub n minus 1? And is that the pattern for every single time? Okay, so this is when recursive is easier, right? It's easier for me to write a recursive formula when I see the sequence already. And it's harder now to write an explicit. But again, explicit is easier to plug back into in the end, right? So let's try and write an explicit formula now. So again, this is your recursive formula. And now I want to try and write an explicit. So how would I write a sub n explicitly? Huh? 3n, right. You can just do 3 times n, because then you'll notice 3 times 1 is going to be 3. 3 times 2, 6. 3 times 3, 9, right? So one thing to make a note of, you guys, is that if you're adding a common term as your sequence, that shows up as multiplication in your formula, right? So keep that in mind. In your explicit formula, I should say. So this is your explicit. Okay, the next one gets just a little bit trickier. So let's first define it recursively, because we know that that will be easier. Okay? So what do I do? So first of all, if I want to base this off of the term right before it, then I'm using a sub n minus 1. What am I doing to a sub n minus 1? Multiplying it by what? Negative 3, right. So I'm actually going to squeeze that in front. So negative 3 times a sub n minus 1. But if I want to write this, so that's recursive, but if I want to write it explicitly so that I can use it better down the road, what is that going to look like? This is where you have to kind of be tricky about it. So if you multiply negative 3, multiple times, let's say that I multiply negative 3 5 times. How can you condense that? Negative 3 to the 5th, right? So technically, I want to be writing the multiplication by negative 3 as a power of how many terms I have, right? But if I plug in 1 right now, so if I plug in a sub 1 and a 1 here, then I have that my first term is a negative 3. Is it? How can I adjust that? So in other words, I don't want this negative 3 on the first term, so what power would be ideal here to get rid of that? A 0 power, right? Meaning that if I'm plugging in n is 1, I want to subtract 1 to force that out to be 0 on the very first term. Do you guys see that? And then, now that this power is 0, that changes this whole thing to be 1, so it's not affecting anything on the very first term, but it'll start affecting things on the second term, right? But on the first term, if I want the first term to be negative 5, all I have to do then is tack on a negative 5. So what that does is for a sub n, or a sub 1, is it zeroes out my power so that this thing doesn't do anything on the very first term. right? And then I can say negative 5. And then when I plug in a sub 2, I'm going to have 2 minus 1 is 1. So then that's my first multiplication by negative 3. And from there on out, as this goes up by 1, so does my power, meaning that every time I bump this up by 1, I'm multiplying by another negative 3. Does everyone follow? Okay, so that is my explicit formula, because as of right now, I could plug in a sub 50 and calculate it right away, right? I could just put 50 in for n and be good to go. Whereas up here, if I wanted to find a sub 50, I'd have to know a sub 49 first. Are there any questions on that? Okay, so these two different types of things have different names. When you have addition between all of your terms, it's called arithmetic, and we use multiplication in our formula to take care of it. When you have multiplication between all of your terms, it's called geometric, and we use powers to take care of that. Are there any questions? So I'm going to sum that up on the next slide here. For arithmetic, we'll do geometric in a little bit here. But a sequence is arithmetic if you can find a common difference so that that's what you're adding on or subtracting every single time. So that from a sub, and you guys will notice that I wrote this slightly different than how I did the other way. It doesn't matter which way you write it. So like if I wrote a sub n, then I would be writing a sub n minus 1 plus d. These are the same. They mean exactly the same thing. This one, in my opinion, is a little bit better because if I ask you to find a formula for the nth term, technically this is the nth term and this one is not, right? That's for the n plus 1th term. So watch out for that. Okay, so what kind of a formula is this? Explicit or recursive? What is it? Recursive because it's depending on the term before, right? So this is your explicit formula. The reason why this one will work is kind of similar to the one we just talked through where we had to do n minus 1 on the power. Okay, if you want a sub 1 to equal a sub 1, right? Then you put a sub 1 there, but then we want to be adding on numbers after that. The common difference you want to be adding on after. But what does this n minus 1 do? Why do I have this here? So that on the first term, when I plug in a 1, what happens? This all zeroes out so that you are left with a sub 1, right? And then I can add my common difference on afterwards now that I'm picking up n's. So that's how you will write an arithmetic sequence, is you will say this is what I want my a sub 1 to be, plus, and then you'll say n minus 1 times whatever that common difference. So let's try writing a few of these. So this one, we want to identify the common difference. We want to write a recursive rule and an explicit rule, and then find the 10th term. So what is your common difference for this one?